Thank you all for joining me for this presentation. So I'll be talking about Android applications and how to keep their sizes in check. My name is Eric, and I'm indeed the developer of ProGuard. It's my open source project, and you may have used it before because it's part of the Android SDK. I'll be mentioning that, of course, in my presentation because it's my favorite topic, but I'll go beyond that. I'll also talk about other techniques that you can use to reduce the size of your applications. I'm currently working at my own startup company where we still develop ProGuard as an open source project, but also work on a commercial extension of that called DexGuard. I'll briefly mention that later on in the presentation. So I'll be talking about applications. You're probably all developers, so you know what is inside an application. You have resources and assets on the one hand, and you have all kinds of code on the other hand. Typically Dalvik bytecode, maybe some native code, maybe some renderer script code as well. In the first part of my talk, I'll be talking about resources and assets, what you can do to keep those sizes in check. And in the second part of my talk, I'll focus on the Dalvik bytecode aspect, where ProGuard comes into play as well. So if you're developing, you may have run into some constraints already. What I present in my talk, you may have done research yourself and come to the same conclusions, but hopefully I'll be able to give you a few more tips and give you some ideas where you can work on if you run into those problems. One of the issues that you might run into is that the overall size of your APK, your application, is limited to 50 megabytes if you upload it to the Google Play Store. It's quite big already, but maybe your application has lots of assets, and then it can become bigger than 50 megabytes, causing these problems. Looking at the Dalvik bytecode specifically inside the APK, there is this infamous limit of 65,000 something method IDs. I'll be discussing that in some more detail later on in my presentation, how you can try to avoid it, and if you can't avoid it, how you can solve it. And then there is an even more obscure constraint in some older versions of Android, the 5 megabyte linear alloc buffer. I won't be discussing that part, but if you're interested in it, you might want to look up the blog by David Rees, an engineer at Facebook, who wrote a very ugly hack, but it's very impressive also solving this problem for those devices. So I'll be talking about the Android build process. Now you can compare that to baking a cake, where on the left-hand side you have the ingredients that go into the cake or into your application. In the center you have the process itself, the baking process. That's my attempt to draw an oven over here. And on the right-hand side you have the output, the cake that comes out of the process, and or the APK in the case of the Android build process. I'm showing this because it illustrates kind of a red thread through my presentation, where you can work on the ingredient side if you're struggling with application size, or you can work on the build process to improve the application size. Now, I'll go into a little bit more detail than that. So this is what the actual Android application build process looks like. On the left-hand side, you start from your input. You have assets, you have XML resource files, text files. You have your Java source code, maybe Groovy source code if you're using Groovy or other languages. And you probably have a series of libraries that you include in your application. Now the build process copies and compiles them to the output on the right-hand side, which goes into the APK file. Notably, the Java source code is first compiled to Java bytecode, and then it's compiled further on to Dalvik bytecode. The compiled Java libraries are just compiled to Dalvik bytecode together with your own source code. Now, let me start with resources and assets. This is kind of obvious what I'm mentioning here, but there are some more formats that are more suitable for putting into an APK if you're concerned about size. Some formats are just more compact than other formats. If you have images, then JPEG is generally more compact than PNG, but it's a lossy format, so it's more suited for images, for pictures. On the other hand, if you have PNG, there are various internal representations that PNG can use. Some of them are more efficient than others, size-wise. And you might notice in your build process that you see a lot of output coming from AAPT, which does exactly this, taking your original PNG and processing it again to a slightly more, hopefully, representation inside. So it's still a PNG, but more efficiently stored. This can usually give you a couple of %. In my experience, it's not that much of a difference. If you're storing audio and video, you have to pick the proper formats, obviously, also. Now, looking at resources, you probably have resource files in the res directory. And as your project grows, you might be adding to those resources to a point where you have lots of them in your project, and some of them at some point might not be used anymore. Some of them are used, and it's a bit of a core to figure out which resources are necessary and which ones aren't. Luckily, there's help for that. You can use the Android SDK itself, the lint tool in Gradle. Will print out all the unused resources in your project. And then it's up to you to decide if you want to remove them or leave them in for now, whatever. There are a couple of open source projects that actually go in and remove those resources for you. One of them even does that on the basis of the output of lint. But more recently, there is also support in the Gradle build tool to actually, during the build process, remove the resources that are unused at that point. What you have to do there is shown in this configuration. It's a matter of enable minification, which compresses code, and I'll get back to that in a moment. And then, in addition to that, you have to enable the shrinking of resources. So what the tool will do at that point is essentially remove unused files like PNGs from the output. If I'm not mistaken, at this point, it doesn't remove the individual entries in your XML files or strings in your XML files, but those are generally not that much of a problem size-wise. If that is not sufficient, you can start actively removing resources or leaving out resources that you don't really need, perhaps. So if you have an application, there's now and you only, and it's becoming too big, and you only want some languages, for instance, you can specify this fairly new option, res configs, which in this case, in the top line, restricts your application to just the English and Polish languages, and it will leave out all the other languages. Or the second line, it will constrain the densities of the displays of the devices that it targets to just generic no DPI and HDPI. That's a bit of a crude method, but in some cases it might be useful. Now, if all of that doesn't work, then you might start thinking about splitting the APK files into several versions, flavors of the file, targeting different devices, maybe different user groups in each of the individual APK files. Looking at it in the Android build process, it's essentially the same, just at the very end, the assets and XML resources are split so that you can create these different APK files, each containing just a part of it and thus being a lot smaller than the combined version. What does that look like? Well, there are a couple of techniques to achieve that. It's the easiest way to go about it is if you use the Gradle build process already. And a bit of a primitive way to do it is to create different flavors in your build file. specify different flavors, and you can specify different ways to get different input in the various output files. For instance, you could create a flavor that has some filter on it, and I'm sort of abusing the filter here to specify only large PNGs in the top and only the small PNGs in the bottom flavor. You could also specify different directories for each of the APKs, but then you also have to manually maintain which resources and assets go into one APK and which resources and assets go into another APK. Or you could use those constraints that I mentioned earlier, where you only specify, to only have certain languages or certain densities in each of the APKs. Now, the Android team realized that this is a bit of a cumbersome way, error-prone way also to create different APKs. So they have created another option more recently to automatically split your input into various APKs based on some criteria. For instance, you can split based on the density again, where you can specify which densities you're interested in, for instance, MDPI, HDPI, XHDPI, and that will create 3 different APKs for you automatically, so just with these few lines. On the other hand, you can also split based on the native code in your application, so then it will be targeted to the different platforms, the different processors. For instance, the ARM processor, the x86 processor, and the MIPS processor. It will again create 3 APKs. And in this case, because I'm combining these options in a single build, it will create 3 by 3, 9 APKs as output automatically. These techniques, they're easy to specify, but Google doesn't recommend them because it takes some more overhead in the build process, of course, and it also takes some administration in the output. The Google Play Store supports it, but it's a bit more work to keep track of your different APKs. They don't really recommend it if it's not necessary. Next, I'll be looking at code size. And this is something I'm interested in myself because I like fiddling with bytecode. And what happens there is that you start building your application, and during the build process, something blows up. And this is a dramatized view of something that happened to me in real life. But I'll show it to you what this looks like in the Android world, where you get some fairly obscure error message about a method ID not being in a certain range. Depending on the version of Android that you use, you might get a different error. But essentially, there's some index being out of bounds. And at that point, the process just stops. It's up to you to solve that. And more and more people are running, more and more developers are running into that because they're using more and more libraries, and they get huge application code, which causes this problem. Now, what is going on behind the scenes? Just a little bit of background here to show you what the Dex file, which is being created in the build process, looks like. So a Dex file contains different blocks with various constants. There is a block with strings, there is a block with types, there is a block with prototypes for fields and methods, and there are also blocks with fields and method IDs, which are essentially the headers of all the methods in your application. This is not only the methods that you write yourself, but also the methods that you invoke from your application. And that's how it can increase quite rapidly if you, even if your number of classes and number of methods is fairly limited still. The most common problem that people run into is that they run out of method IDs, because actually that table of method IDs there, it can be any length. But the problem inside the Dalvik, the Dex format, is that they are indexed using 2 bytes, which is why you can only have this 65,000 something number of method IDs. So developers mostly run into the problem of running out of method IDs, but you can also have the same problem with field IDs if you have lots of resources in your application, and for each of these resources, a field is being created so that you can reference it, a field in the R classes, the automatically generated classes. So I've also seen cases where the number of fields IDs is exceeded. So a first solution that comes to my mind then is to apply ProGuard. And what does ProGuard do? You may have tried it already. It essentially takes your application code combined with your library code, and it applies 3 subsequent processing steps to it. It starts with a shrinking step, which will take the code and remove all unused classes, fields, and methods from that code. And the result is usually much smaller than the original application, especially if you're using libraries in which you only use probably small parts. So the results that you can get there are something like a reduction of 20% up to 90% in bytecode size. In the next step, ProGuard will take that code again and optimize it further. It will go in at a bytecode level, at an instruction level, and try to optimize the individual instructions. It will also inline methods, it will propagate constants, it will remove unused parameters, and so on. And in that step, the code will be, again, reduced in size a little bit, not as much as in the shrinking step, but still. And it will improve the performance, mostly, both for the Dalvik virtual machine and for the ART virtual machine. You can expect a performance improvement of something like 20%, typically. So that's quite a nice benefit there. And in a final step, it will take the resulting code and obfuscate it. And what obfuscation means here is that it will take the original names of classes, fields, and methods, and it will replace those original names by short, meaningless names, A, B, C, D, and so on. And this process, again, will reduce the size of the application code a little bit more, not as much as in the other steps, but still small benefit there. And as a side effect, or as a main effect, maybe it will make the code more difficult to reverse engineer. It will be more difficult to read if you try to disassemble or decompile that code, which, depending on your point of view, might be desirable or not desirable. You can always disable any of these steps in your configuration file. So let's see, where does ProGuard fit in the Android build process? You remember the original process? Well, ProGuard fits right there in the middle of that process, in between the compilation by Java-C to Java bytecode and the compilation from Java bytecode to Dalvik bytecode. So ProGuard will read the original Java bytecode and process it to optimized Java bytecode. It will it will take the original Java bytecode libraries and process those as well. As a small note here, ProGuard also reads a configuration file, which you may or may not need to write or extend, and it will write out a mapping file, which is used in or written out in the obfuscation step, where it writes out all the original names and their corresponding obfuscated names. And that's useful if you ever get any stack traces from your obfuscated application. Then you can recover the original stack traces by looking up the original names in the mapping file. And there's actually a tool that comes along with ProGuard called retrace, which will do that for you, so you don't have to do all of that manually. If you've tried ProGuard before, you probably know how to enable it. In Ant and Eclipse, you have to comment in a line that's already present in the project.properties file. If you're using Gradle, you have to add a couple of lines to your build.gradle process. And I actually forgot the main line here, minify enabled. True is the line that you have to add there. And then you have to specify those two configuration files. There is one generic configuration file for Android, which is taken care of in the Android SDK. And there is a configuration file inside your own project, which is essentially empty to start with. In this example, I've put just the verbose option there to make ProGuard print out some statistics about what it does to your code. In some cases, you might need to add a little bit of configuration to your own project-specific configuration. And that's in the case of reflection, which is the main source of trouble if you're running ProGuard for the first time. Let's see, what does such a configuration look like? And I've tried to make this presentation as practical as possible, so I'm taking a configuration that is used for Dagger, the dependency injection library and framework that you might be using, because I get this question often. It's a fairly complex configuration already compared to other problems, but on the other hand, you can see how compact it still is. What this configuration says is it tells ProGuard that it shouldn't obfuscate or it shouldn't remove or optimize any fields that have Dagger annotations. That's in the first couple of lines. And in the second block of lines, it tells ProGuard not to remove or rename any of the generated files. As you may know, Dagger generates some files automatically, some class files, some classes. And these classes are named $module adapter and so on. And Dagger is based on reflection, or is using reflection to link the original classes with these automatically generated classes. So ProGuard is not allowed to rename those. And you have to tell ProGuard because ProGuard isn't aware of this. And that's how you specify that. In addition, you have to specify the original classes that correspond to those generated classes. In this case, these are the COM example classes that you can find in a sample. In your application, that might be your own Dagger classes that have annotations in them. And finally, you have to keep some internal Dagger class. So that's all you have to do there. It's a common question I get, but it's not all that complex if you think about it a little bit. All the classes and fields and methods that are involved in reflection in Dagger, you have to preserve those, or ProGuard might be removing them or renaming them so that it doesn't work anymore. Okay, so that's working on the build process. But you can also look at what goes into the build process. And an important aspect of what goes into the build process is the libraries that you put in there. And I've created a list of some common libraries that are notorious for having being quite bulky and introducing a lot of method IDs, which is the measure that I've listed here. The most notorious library is probably the Google Play Services library, which by itself has 23,000 something method IDs, which is also already eating up something like a third of the method IDs that you can use in your application. So that's quite a bit. There's also the Guava library, which is quite bulky, and so on, some other smaller libraries. And a special case is the Scala runtime library. It used to have 100,000 method IDs, so you couldn't run Scala without any special measures on an Android device. But now they've split the Scala runtime into several smaller components, and the core component has only a 50,000 method IDs, which doesn't leave you that much room to create an actual Scala application, but it should be possible like that. Now, a first remark here is, as you may know, that recently in recent versions of the Google Play services, they've also split up that huge library into several smaller components. So it's a good idea to start with just the components that you need if you write an app that only uses a few of them, or maybe one of them. If you use, for instance, the Maps API, you'll use the Maps component, and it will automatically include the base component as well. And then you'll get maybe not exactly the sum, but a combination of the method IDs from both of these. Now, you might not always have the luxury of having these nicely split, nicely partitioned libraries. So a solution that comes to my mind again, it's a kind of a hammer and a nail problem, is to use ProGuard on the libraries. So instead of applying ProGuard in the build process, you can also apply ProGuard to the input that you feed into the build process. You can do a kind of pre-processing step, in this case to the libraries, to make those libraries smaller. And that's this ID. So you start from one or maybe more libraries that you take, and you run ProGuard on it, and then you should get a process library that has the same functionality that you can use in your debug builds and in your release builds without any problem. But it's a lot smaller and it will cause fewer problems, and it'll be a bit more efficient also because it's smaller. As an example here, I've taken the Google Play services, the large library in this case, and I've created a custom version of that one with just the ads services in it. And this is what a ProGuard configuration line file for such a library would look like. So this is completely outside of the Android build process. It's pre-processing a library to something that's a lot smaller. So in ProGuard, you tell what the input is. In this place, the Google Play services jar. You tell what the output is. You specify on which libraries it's being built or on which it's based. We're not interested in optimization or obfuscation in this case. I switch off a couple of warnings. And then the fundamental part is that I'm interested in the ads package in the Google library. And I'm interested in all public and protected fields and methods in those in the public classes of that package or those packages. There is a final line which is involved in reflection, which I have to preserve as well. So a special class there. And then I can run ProGuard from the command line in this case, using this configuration files, and within about 3 seconds, you'll get an optimized, custom version of the Google Play services jar. And the result of that is shown here. So originally, the huge library contained something like 23,000 method IDs. The reduced library contains 3,700 method IDs. So that's a lot more manageable already. So it's a reduction by 80%. Even comparing this to the combination of the partitioned libraries that Google provides, this is quite a bit smaller. It's a bit more than 50%, I think. So the reduction is a bit less than 50% if you do the calculations with the other partitioned libraries. I've applied the same principle to the maps library. So the same ID where the Google Play services jar goes into the process, the maps jar comes out. In this case, I needed to preserve the maps package, but also the common package and the location package, all of the public classes and their public and protected fields and methods. And again, in a couple of seconds, you get a result there. In this case, reducing the number of method IDs from 23,000 to something like 5,000, which is quite pleasant to introduce in the build process because it'll be faster and the result will be more compact. This is just an example. You can apply the same principle to your own libraries or other libraries that are quite large. Now, if all of that doesn't work, then you may have to resort to splitting your DEX file. So instead of having a single main DEX file, you'll then have a main DEX file and a secondary DEX file. And the main DEX file will be loaded when you run your application, and it will in turn dynamically load the secondary DEX file. So there are two aspects to this. At build time, you have to split the DEX file somehow. And at runtime, you have to combine, or the code, someone has to combine that back to a single running application. So the principle is simple. The implementation behind it is fairly complex. You could do this manually. There is a blog about by a Google engineer about how to load class or DEX files dynamically, but it's quite complex because it involves, first of all, splitting the DEX file, but also using reflection to call the proper methods in the proper classes. So it's not generally something that you don't want to do manually. I'll show the alternatives in a moment, but this is what the build process looks like. Essentially, it's still the same as always, except at the very end, the DEX file is split into two, but both of those DEX files go into the same application file. The tools that you might use, there have been a couple of open source tools that you may have used in the past, but they're now superseded, I guess, by the new multiDex functionality in the Android SDK, so more specifically in the Android Gradle plugin. I'm also mentioning DexGuard, which is our commercial product. Well, just because I like it so much, I needed to mention it. It has its own functionality to split DEX files, and it uses a different strategy, actually, than the multiDex functionality. What it does in DexGuard, it can be integrated in any build process, but in your project file there, you can write that you want certain classes or maybe entire packages to be put into each their own individual DEX files. And then DexGuard will go in and it will split all of the DEX files, and it will apply the proper reflection to make sure that the invocations between the DEX files still work, and it will also automatically apply the necessary lazy loading of the individual DEX files. So it's quite transparent in the build process, and it has this lazy loading property. A disadvantage is that it uses reflection to invoke to have invocations between the different DEX files. Compare this to the new feature, the multiDex feature. It's quite easy to enable. Also, you specify multiDex enabled true in your build.gradle file, and you also have to specify this additional line in your Android manifest file. What will happen then is that the build process will automatically figure out which classes it wants to put in a separate DEX file. This is a bit of an overhead. It does this automatically. You don't have much control over it. But in the end, you should end up with an APK with their own separate DEX files. An advantage here is that this support library works back in older versions of Android also. They are implementing various hacks that the other open source tools used to use to make sure that they dynamically link together all of the individual DEX files. So this is the latest standard. Maybe a slight disadvantage here is that it uses eager loading. So at the time when you start the application, the main DEX file and the additional secondary DEX file and maybe other DEX files are loaded. So there is a bit of overhead there, tying together all of that code again. Maybe a quick glimpse into the future. I've shown the build process a couple of times where you have the Java compiler and ProGuard in between optionally, and then the DEX compiler to get from your Java source code all the way to Dalvik bytecode. And the Google Android engineering team has been working on streamlining this entire process, trying to go directly from Java source code to Dalvik bytecode. And what they've developed and what's already available in a preview in the current Android SDK is the Jack and Jill compilers. The Jack compiler takes the Java source code and compiles it directly to Dalvik bytecode. Because ProGuard was squeezed in between this Java compilation and in the DEX compilation, that functionality is integrated also in the Jack compiler, so it reads the same ProGuard configuration files and it writes out the same ProGuard mapping files. So for you as a developer, it doesn't change anything really. It's just a streamlined process. The GIL compiler is something that's used to pre-compile your libraries so they can be processed more efficiently by the Jack compiler. If you want to experiment with it, there is also already a flag, use Jack, that you can enable, and it supports all of these additional options like minify enabled, shrink resources, and multiDex enabled. So that almost concludes my talk. But in summary, the ideas are the same for resources and for code, really. You can work on the input side, you can try to reduce the number of ingredients that go into the application, or you can work on the build process. So in case of resources and assets, you can try to compress the input, the resources, or in the build process, you can trim resources that are unused in your application, or if all of that doesn't work at the very end, you can split your APK into multiple APKs for different targets. On the bytecode side, the same story. You can shrink the libraries that go into the application. You can work on the build process to shrink the application itself. And if all of that doesn't work, you can resort to splitting the DEX file into multiple DEX files. This presentation will be online later on, so if you're interested in some further reading, here are some references to blogs and documentation, and to tools, also documentation of tools, which you can find all online. So I guess that concludes my part of the talk. If you have any questions, I'll be happy to answer them. I'll also be around at the conference where you can ask more questions. Thank you.
Oh, thank you. Any questions from the audience?
There's a question there.
So another thing that produces quite a lot of code and methods is protobuf compiler. Does ProGuard can help somehow with that?
I haven't experimented with it in a long, long while, so I don't know the details of that anymore. But essentially, ProGuard can process any Java bytecode as long as you provide the proper configuration. If I'm not mistaken, well, there are two ways to use a protobuf compiler. One is using reflection and one is without reflection, or no?
ProGuard compiler just generates for performance profile a lot of code, really, variables, and for other profiles less code. And the question is if it uses all of it code, the code, or ProGuard can stripe something out. So
my guess is, and my experience really is that ProGuard can always strip out lots of unused code, even in the cleanest designed code. You always have layers of abstraction in your code. You always have small pieces of code that are not used in certain use cases. So generally, I would expect, yes, there could be an effect. But I would have to try it again to be sure. And then it's a matter of making sure that all of the reflection is taken care of in the configuration file.
Do you have any experience using ProGuard with Cordova or PhoneGap, or does it make sense?
I have some experience, yes. We can process it. Does it make sense? Not that much, because it only processes the Java side. So maybe if you have Java plugins, which is possible, I think, in Cordova, then you can process those. Other than that, it won't affect the JavaScript code, the HTML, the CSS, and so on that you have in your actual application in that case. So it will process the framework, but it won't process your own application, which is not Java bytecode. For DexGuard, we've done some additional effort. So there you can actually encrypt your own application, your CSS, JavaScript, and so on. But for processing the Cordova framework, there's not that much to gain. Maybe a bit of size, maybe a bit of performance, but nothing fundamental for your own application.
The DexGuard, your commercial product, right? I have a question. You said that it supports multiDex, right? And we have multiDex basically by Google now.
Yeah.
The question is about security. For instance, I have an application with API endpoints, right? And it's not easy to obfuscate that, right? The endpoint must be there. Is there any? Does DexGuard provides any tools to increase the security by encrypting strings, that kind of stuff?
Yes, DexGuard is focused on protecting the source or the application more. So what it does, it offers string encryption, class encryption, resource encryption, asset encryption. It does tamper detection, signature verification, OpenSSL pinning or SSL pinning. So there's more protection on that side. Other than that, the application that you write remains essentially the same. So if the application contains security holes, DexGuard won't fix them. It will remain essentially the same. That's the goal of all of this processing. You put in some code and you expect to get out code with exactly the same functionality, exactly the same bugs also.
Last question. You said, for example, SSL pinning. It's done while processing Dex file, or it's also ProGuard is a package, right? You can use in your application. So is it it's a part of this Dex processing process, or
yes, it's all done processing the Java bytecode to other Java bytecode, or in the case of DexGuard, going directly to Delphic bytecode because it can do that conversion as well. DexGuard is specialized for Android, and it can do all of the packaging and signing and zip aligning and conversion to Dex also.
As for huge projects build time, what is faster, creating multiDex or running ProGuard to strip to make it 65,000 metadata?
My guess is that it'll be faster to, well, that would be a guess. I'm not sure. multiDex might be faster. It is apparently. I see some heads shaking, but in ProGuard, you can enable just shrinking and leave out the optimization, leave out the obfuscation. And shrinking by itself is quite fast. So that might be competitive. I'm not entirely sure. The end result will be cleaner if you have if you apply all of that in your build process, because you'll have a single Dex file and that will be more efficient on the device. So you're probably talking about during development.
Yes, for debug builds and DDD or something like that.
I think you'd have to try it out for your own project. But you can disable optimization and obfuscation and see how fast it goes.
Thanks.
So I have a question over there.
Yeah.
I'm aware that you are the author of ProGuard, not the Dex application.
Yeah.
But I'm interested why the limit for the method IDs is 2 bytes. Why they cannot simply increase it to 4 byte int or whatever?
Well, this is just my guess because I'm not part of the Android team at Google. That they really care about backward compatibility. So you have all these devices out there, not only the newest devices, but also older devices, less powerful devices. And that they don't see upgrades very often or at all very often. And if you change the Delphic, the Dex format, then all of those devices are out of luck and they won't have any apps anymore. So it's very important to maintain backward compatibility, and that's what this multiDex solution does. So that's a small price to pay for keeping that large audience all around the world.
Okay, I have one more, actually. So between shrinking and obfuscation, you do optimization, but you are producing remapping file. Doesn't optimization actually break reverse engineering
Yes, you may be.
the code, actually remapping the code to what
Yeah,
it
you
was
may be
before.
talking from experience here. So
Not just
indeed, if your code is being optimized and at some point methods are being inlined, and one of these methods throws an exception for some reason, then the resulting stack trace will have fewer lines in it than the original code would have. So sometimes people are confused that they get a null pointer exception from a place where you shouldn't get a null pointer exception at all. Now, the good news is that just a week ago, I've released ProGuard 5.2, which you can download and also integrate in your Android build process. And that version goes through a lot of effort to let retrace, restore everything in the original stack trace. So even if you have a couple of optimized lines in your obfuscated code, retrace will recover all of that and restore it to the original stack trace that you would get from the original code.
Yeah, great, that's good to hear. And last question.
Yeah.
Right at the top.
Hi, Eric. Does DexGuard provide a hooking detection? So what if attacker can just hook system libraries and bypass the SSL pinning? Do you make this type of detections?
There is some assistance to detect, let's see, routing of the device, debugging, some other basic techniques. You can find more of those techniques online also to apply yourself without DexGuard at all. And that combined with tamper detection, where you can detect that the application itself has been fiddled with, protects the code a bit better against reverse engineering. So static attacks by looking at the code, or dynamic attacks by subverting the platform on which the code is running, or by changing the code. So it's the idea there is to provide layers upon layers upon layers of protection to make it a lot more difficult to attack the code.
Yeah, okay, thanks.
I have one more question. Any support for Android libraries, ARRs, in ProGuard?
In ProGuard, during the build process, the AARs are unpacked. So all of that goes into ProGuard and it processes it as usual. There's no problem there. In principle, you could even provide an AAR to ProGuard directly if you create your custom build process, because ProGuard can read jar files, but it can also read directories, zips, ears, wars, and AARs, and nested if necessary. ProGuard can figure all of that out.
Okay, thanks.